This is the second part of the module on natural convection. We have natural convection analysis for flat plate, vertical, incline, and horizontal, as well as for vertical and horizontal cylinder, and finally the sphere. Okay. For vertical flat plate under isothermal condition, remember we have two boundary conditions. It's either constant temperature or constant heat flux. Okay. For the vertical flat plate with constant temperature, yes. Ostrach in 1953 has obtained a solution to the boundary layer equation in the earlier module, in the earlier part 1 of the module. I just flew through over the development of the equations in the boundary layer. You can check them out yourself in the eBook. Yes, but here I'm presenting the solution. It's not available in the eBook, but is given in the reference Incropera, 921 in Incropera. The equation is applicable whether your flat plate is at a higher temperature than the surrounding fluid or at a lower temperature than the surrounding fluid. It's a vertical flat plate for laminar flow. Yes, so we have this equation, which is a function of a Prandtl number, in fact, and the Prandtl number was obtained numerically by Ostrach in 920. So you may use this equation. Your eBook presented 916 is a numerical solution, a simple correlation for the average Nusselt number, where you see here 916, the constant depends on the geometry, as well as whether the body is vertical or horizontal or inclined, while the index is 1/4 for laminar flow and 1/3 for turbulent flow. It's quite simple, yes. All fluid properties are evaluated at the film temperature. Here is defined another important dimensionless number, the Rayleigh number, which is just a product of the Grashof and Prandtl numbers. It's a ratio of the buoyancy forces and to that of thermal and momentum diffusivities. See here, right? So, as with the external force convection, hydrodynamic instabilities also arises in this natural convection phenomena, which cause turbulence. So how do we determine the onset of turbulence? We have the critical Rayleigh number. So unlike the external force convection, we look at the Reynolds number. Here in natural convection, we look at the critical Rayleigh number, which is approximately 10 to the power of 9. So you can determine the location from the leading edge in the case of the heated plate. You can determine the location where the turbulence starts to happen. And for the laminar region, you may approximate the thickness of the boundary layer with that used for the external force convection, 651. You may use that, an approximation to determine the thickness of your boundary layer in this case of laminar flow over a vertical flat plate in natural convection. Churchill and Chu developed a correlation for natural convection over a vertical flat plate for all range of Rayleigh number, from 0 to infinity. Yes, it's given 921 in your eBook. But in Incropera, a better correlation has been presented. You look at 927 in Incropera. So the difference between this and 921 in your eBook is the first term, the value of the first term, as well as the coefficient and the index. So you may use either one, because the second one is an improved correlation. Now, if you know your Nusselt number, average Nusselt number, you may proceed to determine your average heat transfer coefficient, and then from there you can get your heat flux. Yes. The next case is a vertical flat plate under constant heat flux condition. This is the second boundary condition. Yes. You may use the same correlation for the constant temperature boundary condition. However, the film temperature is now taken as this. It's no longer the temperature of the flat plate, it's the temperature at midpoint. Because remember, the temperature is increasing from the leading edge, because this is the case for the constant heat flux condition. It's a big difference there. So you know because it's a constant heat flux condition, what's left is just to determine the temperature. Yeah, here you can use this equation to get the temperature at midpoint of the vertical flat plate. So another reminder, all properties are evaluated at the film temperature, but they are defined differently for the different boundary condition case. Right. So this is table 9.1. It's listed for the different geometry, characteristic length, range of Rayleigh number where the Nusselt number is applicable. Yeah. This is 921 in your eBook. This is a better approximation. It's complex but more accurate, and Incropera suggested even a better one than this 921. Yes. So vertical cylinders. The correlations for a vertical plate can be used for isothermal vertical cylinders of height L if this condition 928 is satisfied. So you may use this correlation, yeah, for vertical plate, yeah, either one of these three, provided you satisfy this equation. The diameter over the length must be equal or greater than 35 over the Grashof number based on length to the power of 1/4. Inclined plates. Now, for an inclined plate, the buoyancy forces have components, yeah, resolved forces in the x, and x is parallel to the plate, and perpendicular is vertical to the plate. Yeah. So we have two cases. We have a hot plate in a cooler fluid, and the second one, a cold plate in a warmer fluid. For case A, where a hot plate is surrounded by a cooler fluid, the heat transfer from the top surface is higher compared to that of vertical heated plate. Why? Because the resolved forces in the parallel to the plate and vertical to the plate encourage convection motion, and this breaks up the boundary layer, causing flume to be generated, yeah, mixing, so less resistance to heat transfer. So for this top plate, the top part of a heated plate, heat transfer is much better than that of a vertical flat plate. Whereas the bottom of the heated flat plate, it is lower compared to the vertical heated plate. So it's inclined, below is lower, above is higher than the vertical plate, yeah, because the fx cosine theta is less for theta greater than 0. Remember, theta is measured away from the vertical here, not the one perpendicular to the plate, but vertical here, as shown with my cursor. Yeah. For case B, where a cold plate is surrounded by a warmer fluid. Now the boundary layer is stable above the cold plate, but it is not below. Yeah. The heat transfer from the top surface is lower compared to that of a vertical cold plate. Yeah, as I said, because boundary layer is intact, it's opposite of this. Whereas at the bottom, the heat transfer is higher compared to that of a vertical cold plate. Yeah, because as the boundary layer is broken up, yeah, so better mixing, better heat transfer. Now, for inclined plates, where the angle from the vertical is larger than equal to 0 or less or equal to 60 degrees, the gravitational term, yeah, in the Rayleigh and Grashof number can be replaced by g cosine theta in computing the plate Rayleigh number and Nusselt number. Only for these cases, there is a top surface of a cold plate. Yes, this one because there's a boundary layer, below is all broken up, and the bottom surface of a hot plate. See, you can see here why it's applicable for using the equations for the vertical flat plate. The horizontal plates. For a heated horizontal plate in a cooler environment, the heated fluid above the plate rises freely, it's unbounded. So as it being heated, yeah, the air next to the horizontal plate is heated up, lighter, rises. Yeah. The heated fluid below the plate is blocked by the plate, impending heat transfer. Yeah. So it's discouraging because blocked by the presence of the flat plate. For a cold horizontal plate in a warmer environment, the opposite happens. Now, because now we have a cold plate, so the fluid next to it transfer, heat becomes cooler, but it cannot rise because of the available warmer fluid high up here. But at the bottom, it's a better mixing, so we have enhanced heat transfer below the hot plate. Equations 922, 923 may be used to obtain the Rayleigh number for the listed cases only. Look at table 9.1. The characteristic length to be used in the equations are just the surface area divided by the perimeter. Now, those are for laminar flow, natural convection. For Rayleigh number larger than 10 to the power of 9, turbulence, the average heat transfer coefficient is independent of L. Can you see how? Discuss that later. Next, geometry, horizontal cylinder and sphere. For flow over a horizontal cylinder under isothermal condition, constant temperature on the surface of the horizontal cylinder, Churchill and Chu suggested a single correlation for a wide range of Rayleigh numbers as long as it's below 10 to the power of 12. Now your Rayleigh number is based on the diameter of the cylinder, not the length. So you have 925 given here. For a sphere, Churchill also recommended 926. Fluid's Prandtl number must be larger or equal to 0.7, and Rayleigh number based on the diameter less or equal to 10 to the power of 11. You notice that if the Rayleigh number approaches 0, then the average Nusselt number approaches constant, which corresponds to heat transfer by conduction between a spherical surface and stationary infinite medium. Okay. Now, combine natural and forced convection. The presence of temperature gradients in the fluid in the gravity field gives rise to natural convection current. So forced convection is always accompanied by natural convection. The error in ignoring natural convection is small for high velocity. Then you can just forget about natural convection and look at forced convection for high velocity. But when there is low velocity of fluid surrounding a body, a solid body, you have to consider the natural convection on top of forced convection. Yes. But how can we determine whether we should ignore or take into consideration natural convection? We have these three cases. Now, if the ratio of the Grashof number based on the length divided by the Reynolds number 222 is much less than 1, free convection may be ignored. 0.4, 0.5, you can ignore it. But if the ratio is approximately 1, you have to perform both forced and free convection analysis. Now, if the ratio is much greater than 1, then forced convection may be neglected and you can just focus on natural convection. There are three types of flows also when they have both forced and natural convection occurring. We have assisting flow, where the buoyant motion is in the same direction as the forced motion, of course, So the natural convection assists forced convection and thus enhances heat transfer. In opposing flow, as the term is quite transparent, the buoyant motion is in the opposite direction to the forced motion, and thus natural convection resists forced convection, consequently decreasing heat transfer. Finally, in transverse flow, the buoyant motion is perpendicular to the forced motion. Transverse flow enhances mixing and thus enhances heat transfer. Okay. That's it for this second part of the module on natural convection.